I'm a petrographer. I work on the microscopy of mudrocks, shales, and I don't often get an opportunity to come and present this kind of information to a really broad audience. I'm going to begin with a slide that draws attention to exploration in conventional reservoirs and how it's actually practiced today. And I put this up here to draw a contrast with what, in fact, we are not currently doing with fine-grained sedimentary systems. The practice of exploration today is a pretty sophisticated enterprise, and it entails the use of both large-scale and small-scale data. And we have, for these kinds of data, paradigms and models that allow us to take this data and to make predictions about sedimentary systems in conventional reservoirs. So for example, at a large scale, people can use large scale data such as the seismic section and a model, a stratigraphic and depositional model, to make predictions about where in a basin the volumes of porous sediment will be found. At a small scale, people can use data from petrography to make predictions about the expected porosity that will be found at a given depth. These kinds of models didn't just spring fully formed, they developed over a long period, and our understanding of depositional systems is founded on work that was done in the late 1960s, when people came to the recognition that an understanding of depositional systems could be used in a predictive manner. This soon combined with the technologies of seismic imaging and 3D seismic to give models of great practical efficacy. It wasn't until the late 90s that people understood the chemistry of these systems well enough to do pore scale modeling. But the point is that today you can go to grad school and learn the details of these kinds of models. We're talking about conventional reservoirs that are in sandstones and limestones. They make up respectively about 25 and about 10% of all sedimentary rocks. What about the other 2/3 of sedimentary rocks, the mudrocks? If you graduate from school today, you probably come away with the idea that indeed mudrocks are a major type of sedimentary rocks. They make up about 2/3 of the sedimentary record, and you probably have the notion that they're fine-grained and clay-rich. And indeed, if this is the only view you have, that's about the only understanding you can come to. And in fact, here's some advice from a famous textbook. They prefer the straightforward use of rock color for mudrock classification. But what could we learn if we looked at them a little closer? Well, the first guy to ever do that was this fellow, Henry Clifton Sorby. He's one of my heroes. He, in the mid-1800s, made the first microscopy preparation for getting light through thin slices of rock. And he then carried out a long career making microscopic observations in rock. And toward the end of his life, he published a paper in 1908 on mudrocks. And I won't read this wonderful quote, but what he says is that mudrocks are incredibly complicated, even from light microscopy. 50 years on, I collect quotes on mudrocks. People were still complaining that yes, mudrocks are complicated, but we know so little about them. And I have a big collection of these quotes. And even as we approach the turn of the 21st century, people were still calling mudrocks terra incognita. And why? Why did we arrive at this situation? Well, you know what? Mudrocks are really, really fine-grained. They are a technical challenge to understand. And nobody predicted what has happened. Nobody predicted that we would be able to extract resources from these kinds of rocks. And therefore, people directed their research attention and the funding for research to those rocks that they thought were important, the limestones and the sandstones, and almost nobody and very little funding, flowed to give attention to mudrocks. Well, this is no longer the case, I'm happy to report. And I would advocate that, in fact, we are in the middle of a scientific revolution in our understanding of Earth's most abundant sedimentary material. And what we now know, and I'm going to show you how it is we know this, mudrocks are in fact a very complex class of materials, and they have heterogeneity that's greater than sandstones or limestones. And although they may contain abundant clay-sized crystals, they are not necessarily dominated by clay minerals, nor by clay-sized grains. And I will go out on a limb. Actually, I don't feel like I'm going out on a limb anymore. These are not so-called resource plays. It's better to think of them as hosting exploration targets. And so here's a fine example of that from my colleagues at the Bureau, and we saw this in Scott's presentation the other day. This is large-scale evidence that, in fact, mudrocks are not homogeneous. And this drilling was conducted really as a sort of grand experiment. Nobody had an exploration model in their head when they set about to drill all these wells. And it was only at the end, when we could turn and then look at the result of all that drilling, that we saw that there were regions here that were sweet spots. Here's the problem with assessing mudrocks, and this is a problem Henry Clifton Sorby had. They really are fine-grained. This is an actual 30-micron slice I've taken out of a backscatter image. And so imagine if you're taking transmitted light and passing the light through this material and looking at it with a light microscope. The light passes through many, 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 many little crystals, and by the time it arrives at your eye, it's carrying a very confusing mass of information. And this puts fundamental limitations on how we can use light microscopy. And this is what we get with light microscopy. You know, I always still begin with light microscopy, but I'll be the first to tell you this is opaque on many, many levels. But we have tools in our toolkit that Henry Clifton Sorby didn't have. And this is a backscattered electron image of a mudrock. And that's a 100 micron scale bar. Clay-sized particles are 4 microns or smaller. And so you can see right here that there are many, many particles. These white things are calcite, the black is organic matter. They're bigger than clay size. But in fact, this is a clay-dominated rock. But what I'm here to tell you is that most mudrocks do not look like this. Most mudrocks look like this. This is Barnett Shale. And what you see here is that it's a very complex assemblage of clay and silt size and even sand sized particles of many, many different mineral compositions. And also there's biologic material in here. It's a very, very complex material. Well, here's a technology that I really like for understanding mudrocks. It's X-ray mapping by energy dispersive spectroscopy. What it does is it takes the energy of the electron beam, and when it interacts with material, it generates X-rays that are characteristic of particular elements. You can use this in both a qualitative way and a quantitative way. And here is an example from the Marcellus. So that's a 6 micron scale bar, and this is the secondary electron, or actually a backscatter electron. You can see those are pyrites. And then there's some minerals here, but in X-ray, you can see that some of them are quartz, some of them are feldspar, some of them are clay. You can actually begin to get an accurate depiction and a clear idea of the grain assemblage that makes up these mudrocks. And here's Barnett. Did you know Barnett is absolutely chalky jam full of feldspars? If we took the clay out of it, it would be an arkose, like a feldspathic sandstone. And anyway, this technique allows us to assess the grain assemblages. Another technique that I really love is cathodoluminescence. And once again, this is done on a scanning electron microscope. You take the electron beam energies, and this time you're looking at interactions with the outer shell electrons. It makes visible light. And so the electron beam shoots through a hole in this very sensitive reflective mirror. The mirror picks up the light, shoots it back here into an imaging amplifier that is much more sensitive than your eye. It can see levels of photon emission that would appear black to your eye. And what CL gets you is that it allows you to see things that are absolutely invisible in other means of imaging. So here again is the Barnett Shale. This little thing right here, it's little, it's 300 micron, is an agglutinated foraminifer. Now this next image, agglutinates, they love low oxygen, and they build their shells out of particles they pick up in the environment. But I'm showing you this because here you see that now we've come to a higher mag view. You can see the quartz here, there's some pyrite. In cathodoluminescence, what you see, you can actually see the little particles that make up the shell of the foraminifer, and you can see that there's dark luminescent quartz that glues them together. In other words, all the quartz is not the same, and this imaging method allows you to see that. And here's cathodoluminescence looking at a carbonate mineral. This again is Barnett Shale. This is one of the carbonate lithologies of the Barnett Shale. There's this little round thing. What is that? That's some kind of fossil. What is it? In cathodoluminescence, we see that that's a calcified radiolarian. It's the radiolaria that were responsible for bringing all the silica to the floor of the Barnett Sea. It's the radiolaria that make it silicious, and here it is. But you see, in cathodoluminescence, you get to see things that you can't otherwise see. Now, here's the most important image I'm going to show you. This is Barnett Shale. This is secondary electron image, and here's the cathodoluminescence counterpart. What you see here is that we have some bright luminescent quartz with an angular shape. That's detrital quartz. That's from outside the basin. It was a grain that probably rolled down some river. But then there's this dark luminescing material on the edge and material that is scattered throughout the matrix. That is orthogenic microquartz. It's quartz that precipitated after the rock was deposited. It's the microquartz that makes the Barnett Shale brittle. It's chert in essence. If you remember chert from undergraduate days, chert is really brittle. The Barnett Shale is an argillaceous chert in part, and we can see that when we use cathodoluminescence. Another technique that has really transformed our ability to see these rocks is actually a sample preparation technique. And like so many of these techniques, we adopted this from the silicon wafer industry. And what happens is in argon ion cross-section polishing, you take accelerated argon ions, you shoot them at your sample, and any topography that's standing up gets whacked off, it gets ablated. And this allows us to cut super flat surfaces. And so here's a mechanically polished shale. I mean, if you saw this, it would actually have a mirror finish, but at this scale, it's really bumpy. So, is that a pore? Is that real, or is that some mechanical damage? Argon ion milling allows us to observe surfaces where we're pretty darn confident that we're not seeing mechanical damage and that the pores we see are real. And so here's an example from the Eagleford. You have these mineral-hosted pores between the clay flakes. Here's an example again from the Eagleford. Here we have an organic-hosted pore system in which many of the pores are contained within a residual hydrocarbon that's filling a foraminifer. And here's another thing that Argon milling has won for us, is an understanding that just how small these pore systems are. This is Marcellus. Most of the pores in here, I think the modal pore size is down around 10 nanometers. That's smaller than the wavelength of light. That 500 nanometer scale bar is the same as the wavelength of this green light. And I won't dwell on this, but we're down in a scale where the physics for modeling what happens in interactions between energy and matter there's some very strange rules that apply at this scale. So if we had an exploration model for Mudrocks, what would we want it to do? Well, I think we would like to predict things like these: the storage, the flow, the source, the type of organic matter. Is it gonna yield oil and gas? And are my rocks gonna have brittle mechanical rock properties? Well, let's take a look quickly at the Barnett Shale and see the sorts of factors that might allow one to predict these kinds of things. And here's some of the lithologic heterogeneity of the Barnett. You can see that it varies tremendously in grain size. These three are the same mag. This is lower mag. One of these is the reservoir rock. One of them is a so-so reservoir rock, and the other two are really lousy. Can you guess which one is which? Dividing my lithologies up in the Barnett Shale, I want to show you just two end members. Over here, we have what I'm for the moment calling a silt-bearing mudstone. In it, the clay, which is here, surrounds these particles of quartz, feldspar, carbonate, whatever. Most of the particles come from outside the basin. Over here, we have a rock in which there's quartz grains, but also this matrix dispersed microquartz. This is essentially a chert cemented argillaceous rock. Seen in cathodoluminescence, you can really see the contrast in these as well. And considering the organic matter content, that also varies a lot. These have primarily terrigenous organic matter, whereas these have really fine-grained organic matter mapped here by the carbon in orange that is primarily marine. So it's a complicated mixing system. We have particles from outside the basin, inside the basin of both silt and clay size. Quartz can potentially dominate in 3 of these, even in the same rock. But here's the thing. Here's some TOC, porosity, and down here is permeability. And I have 5 groups, and I'm just going to draw attention to 2 end members, the silt-bearing mudstone and the chert cemented mudstone. And you can see that both of them have some pretty high TOCs, porosities, and permeabilities. But over here, you get the added benefit that it's oil prone because it has marine organic matter and it's brittle. We have here a simple model for exploration. What you want to do is you want to avoid that extrabasinal influx, find your marine organic matter, and look for siliceous fossils that make your rock brittle. And so up here, which one was it? It's that one. It's the finest grain rock, which tells you something about how different models for exploration in unconventional resources may be. But we have every expectation that these variable grain assemblages should show systematic variations that we could relate to the sequence stratigraphic context, something that we understand very well in conventional systems. And now we have the potential, at least, to apply that to unconventional systems. And so here in green, I've shown those siliceous type rocks, and versus the more the tan, the more extrabasinal dominated rocks. And you know, we would think that these extrabasinal things should be in the parts of the systems where you would find sand in a conventional reservoir. So, you know, we have a lot of things in our toolkit, and every one of them gives us a different insight into some aspect of our geological system at the pore scale. And with X-ray mapping, we have a route to understanding the grain assemblages. With CL imaging, we can understand the cementation. And I think there's, you know, just tremendous potential to, you know, make our quest for exploration models a really tractable problem. And so, you know, to sum up, we know that, yeah, mud rocks look like this, but up close, they don't in fact look like this, but rather they have this tremendous diversity, and we can assess that diversity by looking at the rock. And so there's a lot of research we still need to do, and my last slide is just some speculations on, you know, what do we need to do? We need people who are trained in these kinds of things, and, you know, it's not enough just to know sedimentology. You need to know some petrology, and you need to have an integrated understanding of these kinds of things. And then you need to take people who know how to do these things and put them together in teams so that they can work at different scales. No one person is going to understand every scale. You know, I'm not a sequence stratigrapher, but I would sure like to work with some. And then finally, we have so many tools, we need to bring them out and use them in a really integrated kind of way. So here's some drivers and needs for our further discussion, and with that I'll end. Thank you very much.